So first of all, the concept of internal resistance. When the cell is in use, some energy is lost in the form of heat. You may have noticed this if you touch a battery once it's been used for a wee while. Now, because resistors convert electrical energy into heat, we can model this as some resistance inside the cell. So we can't separate it out. It's not an actual resistor. It's just a chemical process produces some heat. But we can model that as some resistance inside the cell, known as internal resistance. And a realistic cell then would consist of a kind of ideal cell and an internal resistance, small r. And the ideal cell then produces a fixed EMF, known as E. And quite often you'll see this drawn with dotted lines round about them to show the idea that you can't separate them out. Now, in a lot of cases, the energy lost is negligible. In most circuits then we can ignore this, but usually we'd notice it more in high current situations. An example that's often given is if you have a car headlamps which are on while you're trying to start the car and the starter motor is drawing a large current, then you'll see the lights dim sometimes. I'm going to jump around the learning outcomes a wee bit. We'll define some of the concepts before we then go back and fill in the other parts. So the terminal potential difference is given the symbol V. Is the voltage across the terminals of the cell, i.e. what's actually supplied to the circuit. A load resistor, and that's usually symboled as capital R to distinguish it from the small r internal resistance, just means the resistance of the circuit connected to the cell. So in the picture I've drawn it above, I've just got a cell there, I've not connected it to anything. But then when we connect it up to a circuit, that's usually known as putting it under load. The EMF, which is given the symbol E, but also stands for electromotive force. It's a kind of older historical term. Is the energy supplied per unit charge. Now that's the total energy supplied. It includes the energy that reaches the circuit and the energy that's lost as heat because of the internal resistance. Lost volts doesn't have a symbol. I'm going to start a new page. Lost volts is the difference between the EMF and the terminal potential difference. So how much are you losing because of that internal resistance? And the last one we want to define here is the idea of short circuit current. But I think it's probably worthwhile talking a wee bit about open circuits. I'm going to mix in some of the ideas about learning outcome 3 as well. Open circuit, load, short circuit. So open circuit means your cell isn't connected to anything. Just like we drew above, small r, capital E, and these aren't connected to anything. So there's no current flowing, and therefore there's no lost volts. And at that point, V will equal E. The terminal potential difference will equal the EMF. So if you connect a voltmeter across that, then you will measure the EMF. Under load means that your cell is connected to a load resistance, i.e. a circuit. And in that case then, the EMF, so from conservation of energy, the energy supplied, the total energy supplied per unit of charge, will equal the terminal potential difference, so how much is used in the external circuit, plus the potential difference across the internal resistance, which is the current I multiplied by that internal resistance R. That's one of our equations we need to define. That's given in the formula sheet. Another version of that, though, that's quite often useful is if you replace the capital V by I capital R, just Ohm's law, then you can write it as that and then gather together the I terms. Now that isn't given in the formula sheet but can often be useful. And another way, incidentally, of thinking about that is that the small r and the capital R act like a voltage divider. So if capital R is large compared to small r, then most of the voltage will be across the external circuit and you'll not notice the lost volts. It's only when the internal resistance is comparable to the external, the load resistance, that you start to notice. And the final definition then of short circuit is basically when capital R equals 0. Now, it's not something that you would normally encounter. And so it usually happens when there's a fault. So if you think about it in your house, you've often got flexes which run both sides of the circuit together. Okay, the live and the neutral, as it's called in the AC, or the positive and the negative if it was a DC circuit. And if they were to touch each other, then what your circuit looks like is that. Okay, and they're completing the circuit without having to go through any external resistance. So the definition of short circuit is that the load resistance is 0, which means that V is 0 because V equals IR, and therefore at that point capital E is equal to I small r. Now once again, it's not given in the formula sheet, but you need to be able to go through that process. And really what that's saying is that all of the energy supplied by the cell is being applied across the internal resistance. There's nothing in the circuit using up any of that energy. And that will generally result in very large currents. So an internal resistance might be, 0.5 ohms for a small cell. But that would mean for a 3 volt cell, for instance, that you would get a current of 6 amps, which is a large current. That has risks associated with it, because then large currents can result in wires overheating or even going on fire. So that first bit about open circuit really covers learning outcome 3 as well. So now I'm going to go back and do learning outcome 2. It's all about how you would set about measuring. Now you could take a single measurement point, measure a voltage, measure a current, measure the EMF on open circuit and use that to work out the internal resistance. But usually we look at graphical analysis for measuring EMF and internal resistance. There are actually 2 forms of that, but one's much more common than the other, so we're going to focus on that one here. And basically you would set up a circuit then with your realistic cell. you would have a voltmeter across the terminals. Incidentally, it doesn't matter whether you put the voltmeter across the battery or across the resistance in the circuit, because there's only one component here. But then you would normally make your capital R a variable resistor, and lastly you'd have an ammeter in the circuit as well. And then read the voltage and current from voltmeter and ammeter. For a range of resistance R, i.e. the variable resistor. And from that you'll get a range of I and V values. And if we then plot a graph of V versus I, I'm sketching this, not terribly well drawn, then what we'll find is that that graph will decrease. Sometimes you just see it drawn a wee bit decreasing. Sometimes you'll see it drawn all the way down to 0, and that's kind of a by the by, that's short circuit. Remember, I said short circuit capital R is equal to 0, and therefore capital V is 0. But that's usually not the bit that we're interested in. The y-intercept then is when I is equal to 0, which is open circuit. So the y-intercept is capital E. And if we think about the gradient, right, this is a straight line graph, y equals mx plus c. Now our y values here are capital V. And we know that capital V, if we rearrange the formula that we gave previously, can be written as V equal E minus I small r. And if I write that in a very slightly different way, but hopefully you'll see that's still the same thing. And the reason I'm doing that is that my y values are capital V, so there's y. My x values are capital I, so there's x. And this is now in the form of y equals mx plus c, where the m, you can see the y-intercept term is E, and the m, the gradient, is minus small r. So the gradient of this line is minus small r. Now be careful of the minus sign, don't just drop it. You should get a negative gradient, and that's equal to negative small r, and then the minus signs cancel out. Now there's not an outcome to go with this, but there should really be a carry out calculations one, so we'll look at a worked example of using this. So first of all, the internal resistance, to calculate that, we're given that the EMF is 1.5 volts. We're given that the terminal potential difference is 1.4 volts, and we know that capital R is 28 ohms. Now, we're going to have a couple of steps to get to the internal resistance, because the formula which links the internal resistance to stuff we know, E and V in particular, has capital I in it as well. So we're going to have to get capital I before we can then use that to get small r. So first of all, to get capital I can just use V equals IR. So 1.4 equals I times 28, and rearranging that gives me I is 0.05 amps, and then once I've got that, I can plug it in to the formula given in the formula sheet. So 1.5 equals 1.4 plus 0.05 times small r. And rearranging that gives me small r is 2 ohms. Now for short circuit, remember we're changing things now. So now we're saying definition of short circuit is capital R is 0. I can assume the E and small r remain the same. And then to get the short circuit current, I can now use the alternative version of the formula which was given. And that will reduce to just small r. So basically we're saying the 1.5 volts is applied all across small r. So we get I equals 1.5 over 2. 0.75 amps. And then for part C, we're changing things again. So now we've got a new value of capital R again. We can still assume that capital E and small r remain the same. And we're being asked the lost volts. Now to get that we're going to need the current once again. Now lost volts doesn't have a symbol, so once we've got the current we'll deal with that at that point. And if I use the alternative version of the formula again, then I can use that to get I. So I is 1.5 divided by 60 is 0.025 amps. And then the lost volts, let's say, doesn't have a symbol, but it can be calculated. It means the voltage across the internal resistance. So just applying IR to that, then it's the current flowing in the circuit multiplied by the internal resistance is 0.05 volts. So in this example, when you've got quite a large external resistance, 58 ohms, and a small internal resistance of 2 ohms, then that's pretty much negligible lost volts. And final one outcome is the idea of load matching. It's basically the concept if you change the resistance in the circuit, then and measure the power delivered to the load resistance, and what you find is it will peak and then drop off. And the value of resistance, which produces that maximum power, is when the load resistance equals the internal resistance. And this is called load matching. So the maximum power is delivered to the load resistance when R load resistance equals internal resistance. That doesn't mean it's the most efficient, because actually at that point you're going to be wasting a lot of power internally as well. But the main place this does tend to get used is in solar cells, because you're not really bothered as much what's going on inside the solar cell. What you really care about is how much power can you actually get out of it, and that's how much power is delivered to your load resistance. So you often see it in that sort of context.